Okay, welcome to today's explainer. We are diving straight into a massive, deeply frustrating physical wall that the entire tech industry is crashing headfirst into right now. Look, we all want this amazing sci-fi future, right? We want endless computing power, people living in space, electric cars everywhere, and life-saving medical tech. But there's a catch. The cynical, exhausting reality is that all of those cutting-edge dreams are bottlenecked by one literal physical problem. Our computers are just getting way too hot, and we are officially running out of traditional ways to cool them down. And the stakes here? $1 trillion. Yeah, that's with a T. That is the staggering scale we're dealing with. The entire future of our technological progress, everything from this massive AI boom to our global data infrastructure, it all hinges on solving what has quietly become the silicon heat crisis. If we can't figure out a way to get rid of the heat generated by these machines, everything we're building right now just stops. It literally falls apart. We have essentially maxed out what our current hardware can physically handle.
So you might be wondering, why exactly are our computers melting? To really understand this trillion-dollar crisis, we have to zoom way in. Specifically, we need to look at the silicon that makes up the backbone of all computing. Computers run on transistors, which simply put are just tiny little on-off switches. If you want more processing power, you need more transistors. And for decades now, engineers have solved this by making those transistors unbelievably, mind-bogglingly small.
To give you a sense of this exhausting scale of miniaturization that's kept Moore's Law alive, let's track the timeline. Back in 2001, the transistors inside the very first iPod were about the size of a single bacterium. Jump to 2006, the ones in the first Nintendo Wii were roughly the size of a flu virus. And today, they are so small they're barely measurable. In fact, physics is basically telling us that if we shrink them any further, we literally won't be able to control how they switch anymore. We can't build them smaller, and we definitely can't just keep cramming more of them side by side like single-family homes in a crowded neighborhood.
Because we can't spread outward anymore, engineers have started stacking these transistors on top of each other, almost like multi-story apartment buildings. And honestly, this is where the crisis really ignites. Stacking them creates this catastrophic heat trap where the heat has absolutely nowhere to go. You know the traditional cooling methods inside your computer, right? A copper plate tries to spread the heat, sends it through some copper pipes, dumps it into aluminum fins, and then a really loud spinning fan tries to blow it away. Well, that system is completely failing. It's fine for your laptop, but for massive data centers, electric cars, and satellites running nonstop, it is a huge problem.
But material science just brought a wildly unexpected wildcard to the table. We need a heat sink that is astronomically better than copper or aluminum. If you look at thermal conductivity, which is just how fast a material moves heat, aluminum is, it's okay. Copper is definitely better. But look way out on the far right. Diamond. Yeah, diamond moves heat better than almost any other natural material on planet Earth.
Diamond is quite literally the ultimate heat thief. We usually just think of diamonds as being incredibly hard, right? Which they are. They're like 4 times harder than the next hardest natural material. But their hidden superpower is actually thermal conductivity. The molecular bonds inside a diamond are incredibly short and super stiff. So when one atom jostles its neighbor, that ripple travels through the crystal at an absurd speed, moving heat practically instantly. If you take a sharp diamond and press it into an ice cube, it cuts through the ice like literal butter. Not because it's sharp, but because it's instantly stealing all the heat from your hand and driving it right into the ice.
Okay, but we need to make a really important distinction here. We're definitely not talking about taking a giant, shiny, single crystal diamond rock that you'd see in a wedding ring and just super glowing it to a motherboard. What researchers are actually building is called polycrystalline diamond. So instead of growing one giant gem, they're growing millions of tiny diamond crystallites, each one only about the width of a human hair, and bonding them together into this specialized flat sheet built entirely for science.
And this is the part where we kind of have to tear down the romanticized idea of natural diamonds. Because when it comes to saving the tech industry, natural diamonds are actually, kind of trash. Digging them out of the ground is wildly expensive, sure, but they're also filled with trapped pieces of other elements from when they formed deep in the earth. Those impurities actually make them worse at moving heat. On the flip side, lab-grown diamonds are unbelievably pure. They are literally engineered to move heat perfectly. We've gotten so good at manufacturing them that lab-grown is mathematically and physically far superior for this job. So, the absolutely crucial question is, how do we actually cook up these pure, superconductive diamond blankets? Because remember, we aren't just talking about a shiny rock anymore. We're talking about engineering a literal fabric of pure thermal relief. And this brings us to the absolute mad science portion of this explainer. The process they use here is genuinely awe-inspiring.
The method scientists are using right now goes by a highly technical name, chemical vapor deposition. But if we break that ridiculous-sounding term down, it essentially translates to microwaving methane. Yes, you heard that right. Instead of heating up a hot pocket, scientists are using massive, highly specialized machines to essentially microwave gases to recreate the chaotic, high-pressure, molten conditions found thousands of miles deep inside the Earth's mantle. Okay, here is the wild, step-by-step recipe they use in the lab. First, they take a tiny diamond seed, which basically acts as an instruction manual telling the carbon atoms what molecular structure to form, and they place it on a heat-resistant metal puck inside a vacuum chamber. Second, they pump in hydrogen gas to help build the crystal. Third, they turn the whole chamber into a giant microwave, about 10 times as powerful as the one sitting in your kitchen, which blasts the hydrogen into a highly energetic cloud of plasma. And finally, step 4, they inject methane gas, which is packed full of carbon.
The moment that methane hits the plasma, something crazy happens. The gas literally changes color, turning into this bright, glowing green. The unbelievable energy in the plasma just rips the methane molecules apart, separating the carbon from the hydrogen. And then, over a matter of weeks, those liberated carbon atoms literally rain down onto the seed. Atom by atom, they are growing a supermaterial right before our eyes. And the best part? They can grow this polycrystalline structure into virtually any shape we need.
Which brings us directly back to our impending doom of melting computers. By growing these pure diamond sheets into whatever shape they want, engineers are now attempting to grow diamonds directly onto computer chips. As one of the world's leading researchers noted, quote, "If I wrap it around like a blanket, you can make those transistors run cooler, hence way more efficient than otherwise it would be. It is a thermal blanket that pulls the dangerous heat away at absolutely unprecedented speeds."
And hey, just to be clear, this is not science fiction. We aren't talking about a theoretical whiteboard sketch here. The specific model we're looking at, the Nvidia H200, is already operating as the world's first diamond-cooled server. We are literally testing this mad science in live data centers right now.
And the impact is absolutely insane. Listen to this quote regarding a recent test they did in a San Francisco data center. They, quote, "actually doubled the amount of compute coming off a GPU." Just think about what that means for the massive AI boom we're living through right now. If you can double the compute output just by efficiently removing the heat, it means you don't need to build 2 massive, power-hungry data centers. You only need to build 1.
To put the sheer power of this diamond blanket into perspective, you have to look at the numbers. Right now, application developers and hardware engineers are desperate, practically begging for just a 2-degree reduction in temperature to keep their systems from failing. And some of this early diamond blanket research has shown they can drop the temperature of these chips by an astounding 70 degrees Celsius. 70! It is a totally unheard of leap in thermal management.
But keeping data centers cool is genuinely just scratching the surface here. This unbelievably pure, lab-grown material has a whole host of other mind-bending superpowers. Because it can handle extremely high voltages, we might eventually see actual diamond-based transistors. Because it's highly resistant to radiation, it is already being used to shrink and cool electronics on space satellites. And, get this, because it is biocompatible with the human body, it holds massive promise for targeted drug delivery systems. It's just an endless series of huge, if true, breakthroughs.
So we find ourselves at this incredibly poetic crossroads. We are literally mimicking the extreme crushing conditions at the center of the Earth to save the future of human technology. We basically hijacked a process historically used to make shiny rocks for jewelry, completely re-engineered it to create an elementally perfect supermaterial, and now we're using it to solve the biggest, most expensive bottleneck in modern computing.
It's a massive experiment. Nobody knows exactly how far this is going to go or what our computing future will ultimately look like. But the fact that the answer to our tech limitations was literally grown in a high-tech microwave, that is just fascinating. So the big question we have to ask ourselves as we look at the absurd reality of our technological future is this: are we ready to microwave our way out of a trillion-dollar meltdown? Because right now, a lab-grown blanket of diamonds might just be the only thing stopping our technological progress from going up in smoke.